Hello, everyone. This is Greg Ristabin from Olympus. I'd like to welcome everyone today to this webinar on advancements in offshore corrosion monitoring. This webinar will introduce the features and technical specs of the EPOCH 6LT portable flaw detector's corrosion module software option, and will discuss the instrument's benefits for offshore platform corrosion inspections. Our presenter today is Calvin Jury. Calvin is the Senior Product Marketing Specialist for Olympus conventional ultrasonic flaw detectors and thickness gauges. This informational webinar has been scheduled for an hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed personally either by email or phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Calvin. Calvin, take it away.
Hello, everyone. Thank you for joining me. As Greg said, my name is Calvin Jury, and I work with the Portable Flaw Detector product group here in Waltham. And today I'm going to be discussing the EPOCH 6LT's corrosion software module. Here's a brief overview of our agenda. I'm going to go over some of the background to offshore corrosion applications, discuss some of the challenges that face offshore corrosion inspections, and I'll go through some of the details of our new corrosion software module. And at the end of the presentation, I'll attempt to do a brief software demonstration. So some quick background on offshore oil rigs and corrosion inspections. An offshore oil rig or platform is a large structure that supports well drilling, extraction, processing, and the storage of oil and or natural gas. These platforms may be fixed to the ocean floor, or they could consist of an artificial island, or they could be floating. These structures are often very large. They typically contain facilities to house workers as well as facilities to process the raw oil and gas that is extracted. When discussing corrosion inspections on offshore platforms, there are many opportunities for corrosion to occur on an offshore rig. It's a steel structure that's in contact with seawater, and so corrosion is certainly a problem. But one key area that is typically a key area for inspection are the marine risers. Marine risers form the link between the seabed pipeline and topside processing equipment. And the reason why this is such a key area for corrosion is that the risers are in what is called the splash zone, which is the area of the platform that's right above water level. So there's constant wetting and drying, and this combined with potential defects in coatings on the risers can contribute to corrosion. Corrosion is of concern to platform managers and inspectors because it can reduce the wall thickness and threaten the structural integrity of risers. And it's important to assess the remaining service life of aging risers, and this assessment or determination of the structural integrity of a riser is often dependent on corrosion monitoring with NDT technologies. Now, riser structures can vary in structure and material, and the makeup of the riser can help determine which ultrasonic or non-destructive testing method is appropriate. Now, there are a number of NDT methods that are commonly used for in-service risers, in particular to inspect for corrosion. One of the most common and well-known areas are conventional and phased array ultrasonics, but there are also other techniques such as guided wave ultrasonics, eddy current and eddy current array inspections, magnetic flux leakage radiography, infrared thermography, and magnetic particle inspection. And there are costs and benefits to each of these techniques. However, conventional and phased array ultrasonics are often the most convenient and the most cost-effective methods of all these. Now, when discussing in particular, conventional ultrasonic inspections of corrosion, the most common transducer probe that's recommended is a dual transducer. And there's a very specific reason for this. when you're inspecting for corrosion, you're looking at potentially rough and irregular surfaces. The corrosion is sort of an irregular process that can create pitting and other defects that can easily scatter sound away from the transducer. In order to get a good signal with the transducer, you're really depending on a parallel back wall to send the sound back to the transducer. So oftentimes corroded surfaces do not provide this parallel back wall. So in order to overcome this difficulty, dual transducers are typically set at an angle. So you have a transmitting element and a receiving element that are set at an internal angle so that they send the sound in a angled sound path. And this sound path is commonly referred to as a V path. As you can see in the diagram on the right, the sound travels in a V, bounces off of the pits of the corroded surface, and then bounces back to the receiving element. This creates sort of a pseudo focus that improves signal response on rough surfaces. There are a couple other benefits to using dual transducers. One is their ability to inspect high temperature surfaces. The reason why dual transducers are better for high surface material is that oftentimes there is a layer of plastic or other delay line material that's on the front of the transducer face. Because of the internal angle of the elements, there's sort of a gap between what would be the transducer elements and the front of the transducer. So that plastic delay line serves as a coupling device, and it also helps to insulate the transducer elements so that they don't overheat and fail on high temperature surfaces. Dual transducers also enable a potentially higher system gain, and they can provide more stable readings on rough entry surfaces. Now, there are a number of challenges that are specific to offshore corrosion inspections. An offshore platform is often not from the middle of the ocean. They're frequently in very challenging environments. So the equipment that's used by inspectors on these offshore rigs needs to be rugged and suitable for use in these challenging environments. So they need to be drop tested, they need to meet strict ingress protection ratings and environmental ratings. What's more, the areas of the offshore rigs that could be potentially corroded are frequently difficult to access, and occasionally these can require rope access to inspect. And now for rope access inspectors, the size and weight of the equipment is a primary concern. Because they're hanging from ropes and their hands are frequently occupied with safety equipment, a rope access inspector typically prioritizes small, lightweight, and portable equipment. And multi-use instruments are also preferred. If they can avoid carrying multiple instruments with them on the ropes, the more the better. The more efficient their inspection can be, and the safer they can be while inspecting. Now, rope access, generally speaking, has become more and more prevalent, not only in offshore inspections, but in other hard-to-access locations as well. In the past, occasionally, scaffolding was used to reach difficult-to-access areas of offshore platforms, but there are a number of costs associated with scaffolding. For one, it's a large structure that needs to be constructed, so it takes quite a bit of time to put up scaffolding. There's a significant monetary cost associated with that. Now, in comparison, a rope access inspection can be rigged up in a matter of minutes or hours. So there's much greater flexibility. It takes much less time, much less effort to set up for a rope access inspection. And what's more, rope access has an excellent safety record. So this brings us to our latest addition to the portable flaw detector line, the EPOCH 6LT flaw detector. Now, the EPOCH 6LT was designed in part for rope access inspectors. The instrument was engineered to IP65 and 67, which means that it's protected against ingress from dust and jets of water and submersion into water. The instrument is drop tested to mil standard 810G. This is our most lightweight flaw detector. It weighs less than 890 grams or 1.95 pounds. We designed the instrument to be used with a rope access kit. So we sell a soft pouch that attaches to straps and clips so you can attach the instrument to your leg or harness. And it was designed to be ergonomically used while in a harness, so it attaches to the top of your thigh, so while you're sort of in the sitting position in a harness, it's easily accessible. The screen actually rotates into a portrait mode so that while the instrument's strapped to your leg, it can be easily viewed and adjusted. And we provided robust corrosion gauging and flaw detection capabilities to this instrument so that it can be used. So it can serve sort of a dual use as both a corrosion gauge and a fully capable ultrasonic flaw detector. And for these reasons, we think this instrument is particularly well suited for offshore corrosion inspections, especially rope access ones. Now, when discussing conventional ultrasonic inspections of corrosion, there are two main methods, or two traditional methods rather, that are typically used. The first is what we refer to as the point measurement method. This technique typically uses an ultrasonic corrosion gauge or a thickness gauge, much like the 38 DO+. And this method essentially consists of taking precision measurements of remaining wall thickness. And in order to monitor for corrosion over time, these measurements are taken in a defined pattern at a specific location and then repeated, so you can sort of gauge a change in part thickness over time. This method is particularly effective for periodic corrosion monitoring rather, and to take precision measurements of discrete defects. Because the instruments used are designed for taking precision thickness measurements, this is a particularly precise way to measure corrosion changes over time. However, this method is not as effective for identifying corrosion or detecting it initially. Because you're sort of taking spot measurements, you're not covering a lot of area, or not covering a lot of surface area. So it's less efficient for detecting new areas of corrosion. It's also not the ideal method for identifying and sizing corrosion-induced cracking or other flaw mechanisms, because these devices are tailored towards taking specific measurements of a back wall rather than sizing and detecting flaws. Now, the second primary method for UT corrosion inspections is using an ultrasonic flaw detector and treating the corrosion as a flaw mechanism. So you're using a lot of the same techniques as you would for other sorts of flaw detection. And you're scanning for pits and trying to detect corrosion-induced cracks. And now with the flaw detector like the EPOCH 650, you can size and characterize detected defects, and you're better able to detect new areas of corrosion or areas of small pitting or cracking. What this method is less effective at doing is taking efficient, high-precision thickness measurements, and it's less effective for sort of tracking or taking periodic corrosion measurements, rather. So sort of our design philosophy with EPOCH 6LT's corrosion module was to provide an instrument that effectively handles both methods of traditional UT corrosion detection and monitoring. So with the 6LT, we're sort of offering the best aspects of a thickness gauge for corrosion and a flaw detector for corrosion in one instrument. So in our corrosion software, we enable the user to easily switch between our two main measurement modes. We have a precision mode that's modeled after a 38 DO+'s thickness gauging capabilities, and a flaw detection measurement mode, which is essentially a fully functional flaw detector. So with a single button press, you can jump between the two modes and perform both types of inspections. So here we're combining the key functionality of a precision gauge and a flaw detector in one instrument. So our sort of philosophy of use is that the user can be in the flaw detection mode, scan a part for pitting and size defects, and then once a defect is located, you can switch to precision mode to take efficient and reproducible, precise measurements of the remaining part thickness. Now, in order to achieve this workflow that I've described, we have a number of features that the corrosion module offers. The first is automatic probe recognition. So we use this feature on the 38 DO+ thickness gauge, Using any of our Olympus thickness gauge dual transducers with the center pin ID, you can plug the probe into the instrument, the EPOCH 6LT, and the 6LT will recognize which probe is connected. It will display that probe name, and it will automatically load pulsar and receiver settings. And this works for any of our Olympus thickness gauge dual probes. We've included what we're calling a true do zero. So on previous flaw detector corrosion modules like the EPOCH 650, we had a do zero function, but it was limited to one transducer channel pulsing. So now we're using two channels on the 6LT to simultaneously take the zero offset measurement from both elements of the transducer. So what that does is it leads to a more precise and more accurate zero offset calibration that you can do in a single button press. We've included V-path correction. So that V-path, the V sound path that I mentioned before, the problem with that is that the sound path is slightly longer than if you're having a straight distance sound path from the face of the transducer to your back wall. So the V-path correction just uses a bit of geometry to offset that change in sound path so that your thickness measurements are more precise and accurate at different depths. We've included an automatic gain control function that automatically detects your leading edge defect or your leading edge signal and optimizes that signal height for precise and reproducible thickness measurement. So you can repeatedly take thickness measurements at different depths, and you don't have to adjust your gain level. You're going to consistently get a solid leading edge for a back wall, and you can get a precise and reproducible thickness measurement. We've also included a color-coded grid view, so you can create a 2D grid file, specify your number of rows and columns that you'd like to have in your file, and that will customize your grid layout. And then you can set thickness tolerances to lead to a color-coded grid. So, for example, you could set a low thickness range. Anything below that range will be red. And then you can set a high thickness range, so anything that's acceptable. Anything above that range will be green, and anything between the two numbers will be yellow. And then you can have sort of a color-coded grid that gives you real-time visual feedback on your inspection as you're doing it. So a bit more on automatic probe recognition. As I mentioned, it uses the same center pin transducer ID technology as our thickness gauges, which means that we can use the same set of thickness gauge probes as a 38DL plus, for example. And we have support for essentially the full line of Olympus thickness gauge dual transducers. So as I mentioned, the pulsar and receiver are automatically configured, and it displays your probe name at the bottom of the screen. So the nice thing about this is that if you are doing an inspection where you typically have to use more than one transducer, or you might have to switch transducers for different materials or different part thicknesses, you can easily pull out your transducer, switch probes, and the setup is automatically loaded. So you can continue inspecting without having to take the time to reconfigure your pulsar and receiver in the middle of inspection. And the idea here is that it saves you time during your setup process and makes your inspection more efficient if you have to swap transducers. So a bit more on the V-path correction. So as I said, it compensates for the difference in sound path created by the dual transducer's roof angle. And you can see here that this angle here, the sound path traveling from the transmitting receiver, the transmitting element to the back wall and then back to the receiving element, the sound path will be slightly longer, and it won't give you the true thickness of the part. So our V-path correction uses an algorithm to offset for this increased sound path, and the change in sound path kind of varies per your transducer. It's affected by your element diameter, your frequency, the actual roof angle, because the angle of the elements actually varies per transducer. So all this information is stored within the probe ID. So this is also loaded when you just connect your instrument, connect your dual probe to your instrument rather. So there's no extra setup needed. And this feature was traditionally limited to our corrosion gauges and it's only recently been utilized by flaw detectors. So here I have a bit more on our actual do zero process. So as I said, the do zero function is designed to measure the time of flight through the transducer and delay line material, and also the electronic delay, the amount of time it takes for the pulsar to send a signal through the cable, the amount of internal delay associated with the transducer pulsing, and it also affects or compensates for rather any wear in your transducer dual element face. So one of the sort of side effects of having a plastic or composite delay line on the end of a dual transducer is that as you're using it, your transducer face can be slightly worn over time as you're passing it over corroded carbon steel. So as that transducer delay line is worn away, you can change the sound path slightly and lead to imprecise or inconsistent measurements. So by taking a zero offset calibration from both transducer elements every time you connect a transducer and every time you hit the do zero function, because it's just a single button press within the software, it continuously optimizes the transducer and adjusts for that zero offset so you can get consistent thickness measurements. So a bit more on our automatic gain control function. So the automatic gain control is automatically adjusting your gain for optimal thickness measurements. And it uses an algorithm that was used on the 38DO Plus to guarantee consistent and accurate thickness measurements. So it detects the first lobe of a signal and then uses an algorithm to determine the zero crossing point and adjust that lobe height so that you get a vertical leading edge and a consistent thickness measurement. And the real benefit here is that with a traditional flaw detector, if you're scanning for corrosion-related defect and then you find your defect, you then have to adjust your settings to get a precise thickness measurement. So here you can seamlessly go from your flaw detection setup, switch over to your corrosion gauging setup, and then automatically have your gain set to the correct level to take a precise thickness measurement. So that we're really sort of optimizing the workflow from corrosion flaw detection to precision measurement of your defect. So the actual measurement algorithm is different than on a flaw detector. So on a traditional ultrasonic flaw detector, kind of like, or such as the EPOCH 650, we have a few different gate measurement modes. So we have an edge detect that determines the thickness based on when the edge of the signal crosses the gate. There's peak detection mode, which takes your thickness measurement based on the peak of a signal within your gate. Your first peak, which takes the thickness measurement based on the first peak within a gate. And all of these gate measurement modes are somewhat dependent or reliant on a consistent signal amplitude. So what you can have happen is as your signal amplitude varies, and a signal amplitude can vary if your surface inspection is rough or if you have a change in couplant layer, your thickness measurement can vary slightly. And this isn't necessarily a super big deal for flaw detection because oftentimes you're trying to detect and size flaws rather than determine precise thickness measurements. But with corrosion gauging and with corrosion monitoring, getting a precise and consistent thickness measurement is of utmost importance. So by having a consistent thickness reading regardless of your signal amplitude, it improves the thickness gauging ability of the 6LT. So a bit more on the grid. One useful application for the grid view is that you can, if for example you're taking spot measurements in a grid pattern, if that's the inspection that you're doing at the moment, you can set up your grid size in dimensions to match the grid of your inspection. So it just makes it easy to correlate your thickness reading to the point on the part that you're actually inspecting. And then the color coding gives you immediate visual feedback. So if you're inspecting and all of a sudden you get a red reading, you know to go back and inspect that again or to take a note of it. So it gives you real-time immediate visual feedback. So now I'm going to do a brief demonstration of our corrosion software with the EPOCH 6LT. So hopefully now you're able to see my instrument screen. This is a live reading from an EPOCH 6LT flaw detector. So what I'll do first is connect my dual element transducer. I'm using a D790 5 megahertz 3/8 inch diameter dual transducer. So I'll connect it here. And you can see on the bottom of the screen that the probe name has come up, which means that the instrument is recognizing the probe. So first, I will turn on the corrosion software. And the instrument will immediately prompt me to do a do zero calibration. So I just say press enter, and it calibrates for the zero offset. I'll go ahead and turn on the grid mode as well. So I'm going to be inspecting a steel plate with some corrosion on it that's about 0.32 inches thick. So I'm going to set my grid threshold based on that thickness. So anything below 0.2 inches will appear as red, and then anything above 0.3 inches will show as green, and in between the two will appear as yellow. First, let's go into the flaw detector mode. So I'm taking readings on my plate here. I'll perform a quick 2-point calibration. So you can see this instrument is not calibrated yet, but I'm coupled to a 0.2 inch step on my calibration block, and the values drawn up by the automatic probe recognition are already fairly accurate and within a few thousandths of my measurement. But I'll go ahead and perform this calibration real quickly for you. Okay, so you can see that I'm properly calibrated. And now in flaw detector mode, I can couple to my plate, so I can see this is the full plate thickness, about 0.32 inches or so. I can scan along about the same readings until I find a point where I think I found some potential corrosion. So now the reading is at 0.184. I'll switch to corrosion mode. And you can see that when automatic gain control is turned on, the signal is automatically peaked up, and I can go ahead and save into my grid. I'll do a few point measurements, so just to give you a variation. So I can put my transducer down, the automatic gain control peaks up the signal so I can quickly take my readings. Let's take a few. Okay. So now that I've filled up my grid with thickness readings, I can go into my file and review it. So if you go to view the contents of the file, as you scan through the grid, you can see the waveforms that I collected as well as the thickness measurements. And if you're using reporting software, you'll be able to see all these waveforms as well, and you can easily export this to Excel. That essentially is the primary functionality of the corrosion module. Now, if anybody has any additional questions, as I said, please feel free to put them in through the Q&A. And feel free to email me directly. You should be able to get my contact information from the webinar session. And we're happy to answer any questions you have. So just so you know, the corrosion module software will be released by the end of the week. So you'll be able to get that from our public website. And you'll also be able to download it directly from the cloud if you have a Wi-Fi dongle for your EPOCH 6LT. So feel free to stay tuned for more information from us. You should be able to access the software very shortly. So thank you very much for joining.
Thanks, Calvin. On behalf of Olympus, I'd like to thank all the attendees for joining today and Calvin for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thank you again for your interest and for taking the time to attend. We'll see you again next time.